Sampling distributions for means. Just as we saw with proportions, as you take a bunch of sample means of a population, let's say you know that the population mean is mu, and you go in and you collect a bunch of sample means, all possible sample means of a particular size. What ends up happening is that the sample means end up being bell-shaped, and they'll be centered right along the true mean mu of the population. So the significant facts for us are that the X bars will all follow a normal distribution if you know the standard deviation of the population, and their center will be mu. But if you know the standard deviation of the population is sigma, the standard error of the sampling distribution is going to decrease depending on what your n is, and your standard error for your sampling distribution is sigma over the square root of n. Later on, when we do some inferential statistics, we might not know sigma for the population, and so this x is these x bars will be represented by a t distribution, which is also a bell-shaped curve. But for now, assuming we know sigma, these x bars will be normally distributed. The center is mu, so the shape is bell-shaped. The center is mu, the mean of the population, and then the spread will be sigma over the square root of n. So suppose that the heights of women in a population are normally distributed with a mean of 66 inches and standard deviation of 2 inches. So we've seen this setup before, and they're giving us that the mean of the population is 66 inches and the standard deviation is 2 inches, and we've got a normal distribution going on. Previously, we saw questions like this one. Find the probability that a woman randomly selected from this population has a height greater than 67 inches. So we're looking at the probability that one woman selected from this population has a height bigger than 67 inches. So now when we're dealing with sampling distributions, the question's going to change a bit. It looks similar, but there are some very important differences. Now we want to find the probability that 16 women randomly selected from this population have a mean height. So these are very important things to know. We've got an n, a sample size of 16 women, and we're now looking for the probability that the mean height, not just any one height like we had before up here, not just one height, we've now got a mean height is greater than 67 inches. So very similar numbers, but the setup of the question, one being a sampling question. The question now is a sampling question with 16 women, and the previous question just had to do with one member of the population. Based on what we learned in the previous slide, the sampling distribution for the means are going to be normally distributed, and their mean is going to be the same mean from the population, so their mean is going to be 66, but their standard deviation, remember, is going to be the standard deviation over the square root of n. So when you plug in 2 over the square root of 16, you now have a standard deviation of 0.5 inches. So your center is 66 inches, but your spread of the means are going to hug the middle a lot more and not be as spread out as the original population of 2 inches. So now let's solve the first scenario where, again, we know this population has a mean of 66 and a standard deviation of 2 inches. And this is the question where we're just looking at a woman, and so we're trying to find the probability that her height is greater than 67. So we're looking at a bell-shaped curve that is centered on 66, and we've got our standard deviation, first standard deviation there, second standard deviation there. So this will be 68, and this will be 70, and then another standard deviation here, and 66 minus 4 will be 62, there's your 64, and so on. 68. Okay, so these are our x's. And if we're looking for the probability that x is bigger than 67 on this graph, it's going to be this shaded area here. And so we're going to get that using our calculator by using normal CDF. Our left value is 67. Oops. Our right value is infinity. And our mean is 66. And our standard deviation is 2. Again, because we're just looking at one woman, we keep the same standard deviation of the original population. And that gives us a probability of 30.85%. So a pretty good chance that you'll find a woman randomly selected that has a height greater than 67 inches. So again, now we're looking at, in this problem, we're looking at 16 women randomly selected and the probability that they have a mean height. So the fact that we're looking for the probability that they have a mean height greater than 67 means we have to look at the sampling distribution, which we know has a mean. The mean of the x bars is the same 66. That hasn't changed. But the standard deviations of the x bars will get smaller than that 2 inches, and it actually came out to 0.5 inches. So my curve, my bell-shaped curve, is going to be skinnier than the one we had originally. We're still going to have 66 inches, but these are the x bars. But then when we get to 2 standard deviations away, we're at 67. Right here would be 66.5, and then 2 standard deviations away over here would be 65. So now when we're looking at this, the chance that the means are greater than 67 is going to be this area here, which is a lot smaller than in the previous problem. And it makes sense that the chance of the mean of 16 people being having a mean height greater than 67 is going to be smaller than just one person being taller than 67 inches. So, but the way we're going to solve it is pretty much the same, just making sure that we account for that smaller standard deviation. My mean is 66, but my standard deviation is now 1/2. And the chance of this happening is 0.0228. So here we just have a 2.28% chance that the mean height of 16 women is bigger than 67 inches. So that's what we mean by a sampling distribution for the means.